The nature of time. Time is something every one of us experiences, yet it remains among the most mysterious elements of our universe. We use time to organize our days, track changes, and measure motion. But what exactly is time? Scientists, philosophers, and thinkers have debated this question for centuries. Some regard time as a basic component of the universe, while others argue it might be just a construct of our perception. To better understand time, we must examine how it behaves and why it feels so intuitive yet so puzzling. We commonly think of time as a linear path from the past through the present and into the future. This concept fits our daily experiences. Clocks tick forward, we grow older, and events unfold one after the other. Although this straightforward view has served humanity well for most of history, modern science suggests that it might not tell the full story. Take Einstein's theory of relativity, for instance. It revolutionized our view of time. According to relativity, time is not a standalone entity. It merges with space to form a single fabric known as spacetime. This unification implies that time isn't uniform. It can stretch or compress based on circumstances. Imagine holding a clock while standing still, and your friend is aboard a fast-moving spaceship with another clock. When you later compare the two clocks, you'll find they display different times. This phenomenon, known as time dilation, has been proven through various experiments. The faster you move, the slower time progresses for you compared to someone who is stationary. Even more intriguingly, gravity influences time as well. Strong gravitational fields slow time down. Scientists have measured this effect near massive bodies like stars or planets. Even on Earth, time ticks slightly faster on mountaintops than at sea level because gravity is weaker at higher altitudes. These findings reveal that time isn't the rigid, unchanging force we once believed it to be. It's flexible. In fact, some researchers go further and propose that time might not be fundamental at all. Instead, it could be an emergent property, something that arises from deeper, more basic processes. Think about temperature. Temperature doesn't exist on its own. It's the result of countless molecules moving and interacting. Similarly, time might emerge from microscopic interactions among particles and forces. Although still theoretical, this concept offers a fresh perspective on what time might actually be. Quantum mechanics, which explores the tiniest components of the universe, presents even more surprises. At this microscopic scale, conventional rules of time seem to break down. In our everyday world, causes lead to effects in a predictable sequence. But in the quantum world, events can appear random, and particles can exist in multiple states simultaneously. This leads some scientists to wonder whether time, as we know it, exists at all on the quantum level. If it doesn't, perhaps time is merely a product of our perception, something that only appears real in the larger, observable world. Our perception adds yet another layer of mystery. Humans experience time linearly, moment by moment, but this could be a result of how our brains work, not a reflection of reality itself. Research suggests our sense of time is tied to memory and anticipation. We recall the past and imagine the future, creating the impression of a forward flow. Without this mental framework, our experience of time might be entirely different. Cultural differences further highlight how flexible our concept of time can be. In English, we often describe the past as behind us and the future as ahead. Yet in some cultures, time is visualized vertically, with the past below and the future above. These differences indicate that time isn't just shaped by physics, it's also influenced by language and cultural perspective. Another fascinating question concerns time's beginning and end. Is time infinite, stretching endlessly in both directions? The Big Bang Theory suggests the universe began around 13.8 billion years ago, raising an intriguing question. Did time itself begin at the Big Bang? If it did, what existed before? Some scientists argue that asking what came before time started is meaningless, like asking what's north of the North Pole. Others propose that time might be cyclical with no true beginning or end, just an eternal loop. Among the strangest theories is the idea of block time. This concept suggests that the past, present, and future all exist simultaneously, like a frozen, unchanging block. In this model, time doesn't flow. All moments are equally real, and our sense of movement through time is just an illusion. This idea challenges everything we assume about time. If all moments exist at once, does that mean the future is already set? What happens to free will? These philosophical questions don't have clear answers, but they illustrate how deeply the nature of time is connected to our understanding of reality and ourselves. Time is also essential to the second law of thermodynamics, which states that entropy, or disorder, tends to increase. This law gives us the arrow of time, pointing from a more ordered past to a more chaotic future. Without this arrow, time might feel directionless, like space. But some scientists question whether this arrow is a fundamental feature of time or merely a result of how we observe the universe. While the scientific aspects of time are crucial, time also has a deeply emotional and personal side. We measure our lives in hours, days, and years, but our experience of time varies with emotion. Joyful moments seem to fly by, while painful ones feel endless. This subjective nature makes time hard to define in purely objective terms. The true nature of time may never be fully known. It could be a core element of the universe, a byproduct of deeper forces, or even an illusion shaped by our consciousness. Each possibility invites us to rethink our role in the cosmos and how we engage with reality. What's certain is that time is far more than just ticking clocks and changing seasons. It is a profound mystery, touching every corner of our existence, from physics to philosophy. Ultimately, time may not have one simple definition. It could be many things at once, depending on perspective. This complexity makes time one of the most fascinating and perplexing aspects of existence. Whether we're charting planetary orbits, probing subatomic particles, or contemplating our own memories, time remains central to the human experience, and its mysteries continue to stir wonder, curiosity, and awe in all who seek to understand it. Origins of magnetic fields. Magnetic fields profoundly influence the environments around them. They shield planets like Earth from harmful solar radiation and give rise to the beautiful auroras at the poles. Additionally, they steer charged particles in space and affect the behavior of plasma and stars. But to understand the origins of these magnetic fields, we must examine the deep internal dynamics of these celestial objects, looking into how materials move and interact. Magnetic fields are produced by moving electric charges. This principle comes from a fundamental law of physics known as electromagnetism. Within planets and stars, these charges are carried by conducting materials such as molten metals or ionized gases, which move in certain ways. To grasp this, think of stirring a pot of soup. When the soup is still, not much happens. But as soon as you start stirring, you create swirls and motion patterns. In a similar way, in planets and stars, the materials capable of conducting electricity swirl around, and this movement can produce magnetic fields. On Earth, the magnetic field originates through a mechanism called the dynamo effect. Earth's core is composed of iron and nickel, with its outer core being in a liquid state. This liquid metal moves due to the heat coming from the solid inner core and the planet's rotation. The heat initiates convection, a process where hotter material rises and cooler material sinks, creating a churning motion. Earth's rotation complicates this further, causing the liquid metal to spiral in specific patterns. These spiral flows generate electric currents, and those currents produce Earth's magnetic field. However, this field isn't static. It evolves over time as the core's motion shifts. Occasionally, the magnetic field even flips, switching the positions of the magnetic north and south poles. These reversals have happened repeatedly throughout Earth's history, though they unfold over thousands of years and don't pose immediate threats to life. Scientists learn about these historical changes by examining rocks that recorded the direction of Earth's magnetic field at the time they formed. This helps us study long-term magnetic behavior and better understand Earth's inner workings. Other planets in our solar system also possess magnetic fields, though they differ significantly. Take Jupiter. Its magnetic field is far stronger than Earth's. This strength is due to Jupiter's core being enveloped by metallic hydrogen, a form of hydrogen that behaves like a metal under immense pressure. Combined with Jupiter's rapid rotation, this contributes to a powerful and extensive dynamo effect. In contrast, Mars has a very weak magnetic field. Scientists believe this is because Mars no longer possesses a liquid outer core, meaning the dynamo effect has ceased. Without a protective magnetic field, solar wind stripped away much of Mars' atmosphere over time. In stars, magnetic fields form through a similar mechanism, but on vastly larger scales and with different materials. Stars, such as the Sun, are made primarily of plasma, a state of matter in which electrons move freely, unbound from atoms. Plasma conducts electricity very effectively. The Sun's magnetic field is generated by the motion of this plasma within its internal layers. As plasma circulates and the Sun rotates, electric currents form, giving rise to its magnetic field. The Sun's magnetic field is neither simple nor stable. It undergoes an 11-year cycle, during which the Sun's magnetic poles flip, similar to Earth's field reversals, but on a much shorter timescale. This solar cycle also influences activity like sunspots and solar flares. Sunspots are regions where the magnetic field is particularly intense, while solar flares are sudden bursts of energy resulting from magnetic field disruptions. These solar events can impact Earth by interfering with satellites and power grids. Other stars, especially those more massive than the Sun, also possess magnetic fields, and often more complex ones. Their rapid rotation and turbulent interiors give rise to intense magnetic fields that influence their behavior, including how they shed mass and interact with nearby celestial bodies. In extreme cases, when massive stars explode in supernovae, their magnetic fields can become extraordinarily powerful. This can lead to the formation of magnetars, a rare type of neutron star with magnetic fields so intense they can distort atoms and molecules, tearing them apart under extreme conditions. The processes that create magnetic fields in planets and stars are intricate, but scientists investigate them using a blend of observations, experiments, and computer simulations. For example, Earth's magnetic field is studied through satellite data, and ground-based instruments. In labs, researchers simulate the conditions of Earth's core to observe how liquid metals behave in similar settings. For stars, telescopes that detect light across a range of wavelengths help scientists observe magnetic phenomena such as sunspots and flares. High-powered supercomputers simulate plasma motion and predict the formation and evolution of magnetic fields. Understanding the origin of magnetic fields isn't just a matter of curiosity. These fields are vital in shaping planetary and stellar environments. On Earth, the magnetic field shields life from damaging cosmic and solar radiation. Without it, our atmosphere might have been stripped away, just like on Mars. In space exploration, knowledge of magnetic fields helps scientists design spacecraft and satellites that can endure space weather, including solar flares. On a cosmic scale, understanding magnetic fields in stars helps us learn about the life cycles of stars, how they form planets, and what conditions might allow life elsewhere in the universe. Magnetic fields also relate to broader areas of physics and astronomy. They connect to the origins of planets and stars, the behavior of plasma under extreme conditions, and even the structure of galaxies. Through the study of magnetic fields, scientists gain deeper insights into many fundamental questions and expand our understanding of the cosmos. Even though we've made substantial progress in figuring out how magnetic fields originate in planets and stars, many questions remain unanswered. For instance, the exact mechanisms by which turbulence in a planet's core or a star's plasma leads to magnetic field generation are still under investigation. The relationship between magnetic fields and the rotation of a star or planet is also a dynamic area of research. As scientists continue exploring these mysteries, they'll uncover more about the forces that shape both our planet and the universe at large. Origin of life. For centuries, unlocking the origins of life has meant journeying back billions of years to a time when Earth looked nothing like it does now. Back then, our planet was a hostile and alien world, devoid of plants, animals, or people. Yet, from this barren and extreme environment, life somehow managed to appear. The mystery lies not only in where life came from, but in how lifeless molecules could have arranged themselves into something living. To explore this, scientists must draw on evidence from chemistry, biology, geology, and physics. Earth formed about 4.5 billion years ago. In its earliest phase, it was a seething ball of molten rock, under constant bombardment by asteroids and comets. Over time, the planet's surface cooled, forming a solid crust. Water began to accumulate, creating oceans. These early conditions set the stage for the chemical reactions that may have led to life. Researchers believe the environment of early Earth was critical to life's emergence. The planet had water, energy sources such as sunlight and lightning, and an atmosphere made of simple gases like methane, ammonia, hydrogen, and carbon dioxide. These ingredients could have reacted together to produce life's fundamental components. One of the most well-known ideas about life's beginning comes from an experiment conducted in the 1950s. Scientists Stanley Miller and Harold Urey set out to test whether Earth's primitive atmosphere could generate organic compounds. They combined gases like methane and ammonia in a closed setup, added water to represent oceans, and sent electrical sparks through the system to mimic lightning. After a week, they discovered amino acids, key components of proteins, had formed. This discovery was groundbreaking because it demonstrated that, under certain conditions, simple chemicals can become more complex. However, amino acids alone do not make life. The next challenge was understanding how these molecules assembled into something alive. Living things are made of cells, which depend on vital molecules such as proteins, DNA, and RNA. Each of these performs different but crucial roles. Proteins are like tiny machines that carry out cellular tasks, while DNA and RNA are responsible for storing and passing on information. One of the toughest questions in the origin of life is, which came first? Did proteins form before DNA and RNA, helping to create them? Or did RNA come first, since it can both carry information and do simple chemical work like proteins? This question sparked the theory of an RNA world, where RNA may have been the earliest form of life. RNA can replicate, store genetic information, and even act as a catalyst for chemical reactions. If RNA did appear on early Earth, it might have served as a key step on the path toward life. But how could RNA, or proteins, form naturally without external help? To answer this, scientists examine early Earth's chemistry and geology. Some believe the planet had natural laboratories where such reactions could occur. Hydrothermal vents on the ocean floor are one example. These vents emit hot, mineral-rich water from deep inside Earth's crust, possibly creating conditions suitable for forming complex molecules. Another idea suggests that shallow ponds or clay surfaces on land may have concentrated organic molecules, increasing the chance that they would interact and form larger, more organized structures. These scenarios show that specific environments could have helped push chemistry toward life. Once basic building blocks were in place, the next big step was assembling them into more organized systems. In today's life, cells are enclosed in membranes that separate their interior from the outside world. This separation is vital because it allows cells to control their internal environment for survival and growth. Scientists think primitive versions of membranes could have formed on their own. Fatty molecules, common in life, can spontaneously arrange into bubble-like shapes when mixed with water. These structures can trap other molecules inside, creating tiny environments where chemical reactions might happen. If these reactions allowed the bubble to grow or divide, it might resemble a very primitive form of life. Yet, even with all these ingredients in place, the transition from chemistry to biology remains one of the greatest scientific mysteries. Life is more than just molecules. It's about those molecules interacting in a way that sustains themselves. To be considered alive, something must grow, reproduce, and evolve. Scientists believe evolution may have started at the molecular level. For instance, if an RNA molecule began making copies of itself, some versions might have done it slightly better than others. Over time, these tiny differences could lead to more efficient, complex systems. This idea connects the origin of life with the same process, evolution, that shapes all life today. Another fascinating theory proposes that life didn't begin on Earth at all. Some researchers suggest that life's building blocks could have arrived from space. Meteorites and comets often carry organic molecules, including amino acids. If these landed on early Earth, they might have contributed to the chemical reactions that created life. This idea, known as panspermia, doesn't explain how life started, but it suggests that the ingredients for life might be widespread in the universe. The question of how life began isn't only about the past. It also influences how we think about life elsewhere. If life emerged from basic chemicals here on Earth, then similar processes could be possible on other planets or moons with the right conditions. For instance, Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, both have underground oceans that might host life. Mars once had liquid water, and scientists continue to investigate whether it ever supported life. By understanding how life began here, we get better clues about what to search for beyond our world. Even after decades of research, many pieces of the puzzle remain missing. Scientists are still testing theories and examining clues from ancient rocks, lab experiments, and even space missions. The origin of life remains one of the deepest and most exciting mysteries in science. But every discovery brings us closer to grasping how Earth's astonishing diversity of life began. The journey is ongoing, and it reminds us how much there is still to learn about where we come from. Life's beginnings tie us to the chemistry of the cosmos and the ancient conditions of our planet. For as long as humans have gazed at the stars, we've wondered whether we're alone. Fast radio bursts, fast radio bursts, or FRBs, represent one of the most captivating mysteries in contemporary astronomy. These phenomena are extremely brief yet incredibly powerful flashes of radio waves, lasting only a tiny fraction of a second. Despite their short-lived nature, they emit an astonishing amount of energy, comparable to the energy the sun produces over several days. The first FRB was discovered in 2007 by scientists analyzing data from a radio telescope. Since then, hundreds have been identified, yet their exact origin continues to elude us. FRBs fascinate and puzzle researchers because the mechanisms behind them remain largely unknown. To grasp why FRBs are so baffling, it helps to understand what radio waves are and how they function. Radio waves are a form of electromagnetic radiation, similar to visible light, but with much longer wavelengths. They move through space and are detected by radio telescopes, which are massive antennas capable of capturing faint signals from distant cosmic sources. What makes FRBs particularly challenging to study is their unpredictable nature. They appear without any warning, then vanish almost instantly. This fleeting behavior makes them incredibly difficult to analyze, let alone trace back to their exact point of origin. One of the most astonishing aspects of FRBs is their sheer energy output. To put it in perspective, imagine a flashlight that suddenly emits as much brightness as the sun. And now imagine all that power released in just a millisecond. That's the level of energy we observe with an FRB. For such a brief event to emit that much energy, something extraordinary must be taking place. Scientists have been working to determine both the source and cause of FRBs. One significant clue is that some FRBs originate from distant galaxies. As radio waves traverse space, they pass through various gases and dust, which causes a phenomenon known as dispersion. This effect causes higher frequency radio waves to arrive slightly ahead of the lower frequency ones. By measuring this time delay, researchers can estimate how far the FRB has traveled. In many instances, the calculated distances are billions of light years, implying that their sources are unimaginably remote. This suggests that ordinary cosmic occurrences are unlikely to be responsible. Whatever produces FRBs must be immensely powerful. One hypothesis is that FRBs are generated by neutron stars, the incredibly dense remnants of massive stars that exploded in supernovae. Neutron stars are so compact that just a teaspoon of their matter would weigh billions of tons. Some of these stars have immensely strong magnetic fields and are classified as magnetars. Occasionally, magnetars release sudden, massive outbursts of energy when their magnetic fields twist or rearrange. Such activity could potentially explain the intense radio waves detected as FRBs. Another possible explanation involves black holes. When matter falls into a black hole, it can unleash extreme bursts of energy. This process might produce radio waves strong enough to be identified as FRBs. Some scientists also suggest that FRBs could stem from collisions between neutron stars or between a neutron star and a black hole. These cataclysmic mergers release vast quantities of energy, which might be sufficient to generate the powerful radio waves we observe. Intriguingly, while most FRBs are one-time occurrences, a few have been observed repeating, emitting multiple bursts from the same location. This makes the mystery even deeper. If an FRB repeats, it effectively rules out one-time events like star collisions. Instead, it implies a source capable of generating energy bursts multiple times. Magnetars, again, are plausible candidates. However, it remains unclear why some FRBs repeat and others don't. Adding to the complexity, scientists have found repeating FRBs that seem to follow predictable cycles. One particularly notable repeating FRB bursts approximately every 16 days. This kind of regular timing is rare in astrophysical events and has inspired some innovative theories. One such idea is that the source of the FRB may be orbiting another celestial object, like a star or a black hole. As the source moves closer to or farther from Earth during its orbit, the signal might become stronger or weaker, creating the periodic pattern observed. Although these natural explanations are compelling, some have proposed more exotic possibilities. For instance, a few suggest that FRBs might be signals from extraterrestrial civilizations. If a technologically advanced alien species wanted to transmit a message across the galaxy, powerful radio bursts might be a feasible method. While this theory is highly speculative, it emphasizes how much we still don't know about FRBs. It's important to note, though, that most scientists favor natural explanations, since these can be rigorously tested and supported by evidence. Still, the idea of alien involvement keeps the conversation lively and open-ended. Detecting and studying FRBs requires specialized equipment. Radio telescopes are the primary instruments used to catch these fleeting signals. Significant FRB discoveries have come from observatories like Parkes in Australia, Arecibo in Puerto Rico before its collapse, and the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. CHIME has revolutionized FRB research. Its ability to observe large swaths of the sky simultaneously has enabled it to detect multiple FRBs daily. This has greatly expanded the catalog of known FRBs and given scientists more data to analyze. One of the toughest challenges in FRB research is pinpointing their precise location. A single radio telescope can only provide a general direction, not an exact spot. To narrow this down, astronomers use a method called very long baseline interferometry, which involves multiple telescopes positioned across the globe. By comparing the signals received at different locations, they can triangulate the FRB's position and trace it back to its host galaxy. Once a galaxy is identified, astronomers can examine it using other types of telescopes, like optical or X-ray instruments, to gather clues about the environment that might produce an FRB. Despite all these efforts, major questions remain. Are all FRBs caused by the same kind of event? Or do they stem from a variety of sources? Why do some repeat while others don't? What determines the strength and frequency of each burst? Answering these questions will take more time, more observations, and possibly new technology. FRBs remind us that even with the incredible strides we've made in understanding the universe, there are still many cosmic phenomena we barely understand. They are evidence that the universe still holds secrets, surprises waiting to be discovered. Each new piece of data brings us a little closer to understanding FRBs. But for now, They remain one of the most mysterious and mesmerizing phenomena in modern astronomy,